All right, you are in the right place for the mechanical noise webinar. We'll be starting in about a minute. We'll start here in another half a minute. You can, at any point, just feel free to chat, ask questions. I'm going to just look up one thing before we get going. All right, time to get started. So just to respect the time of those who are with us, I will get going here. I guess if anyone, again, feel free to just type into the chat. See if I can get those chats. If you have any questions as I go, if you want me to go slower, if you want me to touch on any certain issue. But let's get started here. So the goal is to deal with HVAC noise sources, paths, and mitigation measures. And I'm going to cover some terminology, design criteria, configuration, some of the different controls of the different noise sources and how they can be treated. So first, just to get a few definitions out of the way, duct-borne noise is the noise from the fan through the duct to the supply grills, or duct-borne can be the return path as well. From the registers, or if it's an open plenum, you know, that would be a path as well. But that's going right to those grills. Breakout noise is noise that's coming out of the ductwork. Break-in noise would be noise going, of course, into the ductwork. But it's something to consider, especially when you locate silencers. The break-in can be an issue. Crosstalk would be the path between two different I guess, grills, supply grills. And that can be an issue office to office. We had this issue in prison cells that unless you attenuate that path, that can be an issue in certain environments. And then radiated noise is the radiated from the unit, whether it's rooftop unit or in this case, we have in a mechanical room. So those are the main paths we're looking at. Criteria, generally, we are looking at, or we use ASHRAE, American Society of Heating, Refrigeration, and Air Conditioning Engineers, quite the name. They give us some criteria for determining if the room is, or what type of room should have what type of noise level. I guess here are some examples. So noise criteria, there's generally three different statistical levels we look at, or just levels we look at. The dBA noise level is just the sum. It's logarithmic levels, but it's the sum of the levels in the different octave bands weighted for how the human ear perceives noise. Not all noise is perceived equally. So they came up with this A-weighted level that we're actually more tolerant of low frequency, like diesel, you know, low frequency engine noise. than we are of whistling a high frequency, above 1,000 hertz. So they came up with a criteria or a curve that says, all right, for this level at this frequency is equivalent more or less to a different level at a different frequency. They weight those according to how we hear them, and then they sum them up, and that gives you the A-weighted level. The noise criteria is a little different. They have these curves, and this is a small figure here, but the octave levels are plotted, and you just pull off the highest curve that's been touched. So they're not going to track equally dBA and NC, but there are some published guides that give you more or less a correlation between the two. Because you could have just one spike, in one frequency, everything else being low and it's touching this curve, or you could have everything up against this curve, and the A-weighted and NC would be off a little bit. RC, they have two different criteria. So again, you plot, this doesn't deal with lower frequencies, so RC is generally preferred. They go down to 16 hertz, so it gets the real rumbly, low frequency noise. The NC rating is actually the average of the 500, 1,000, 2,000 hertz bands, and that's where speech generally is. And that's where we're most sensitive. So they average those levels. That gives you the RC. And then you draw two lines, two parallel lines for the low frequency noise, 5 dB above, and for the higher frequency noise, 3 dB above. And then they have little descriptors. Either the noise is hissy, rumbly, neutral, or tonal, or RV would be rumbly and rumbly vibration. So they want it to be neutral would be the goal, but a lot of times you'll find when you plot, it could be hissy, could be rumbly. But those are the things you're looking at. There's two different issues that we'll be addressing. One is evaluating in the design phase, which is always preferred. You can figure out what needs to be done ahead of time, and then evaluating after the unit is constructed and try to fix things after the fact. So of course, it's easier to come up with mitigation to meet the design goals of neutral. But unless but if you do go out and measure, sometimes you will find issues that make it a problem. Mechanical system configuration. So the equipment room, of course, location, you don't want it near any noise sensitive areas if possible. Wall design, vibration isolators, those are all going to be issues. And sometimes you can't help it, space constraints, there's other constraints. And so that we have to do, just take extra care with the mitigation. Sometimes we have to float a floor to get sufficient vibration isolation, or put in additional silencers, or put in silencers that'll help reduce the noise if it's close to noise sensitive areas. Fan selection, one of the biggest issues is just that operating efficiency. If it's under or over, noise wise, that's not the best, but the type, speed, the size will affect the noise characteristics. And manufacturers generally will provide noise levels, octave noise levels, and that's what we'll use for our predictions. And they give us discharge side noise, inlet noise, and radiated noise, but sometimes they won't. And we just have to use ASHRAE tables given the size, the type. We'll come up with something that's similar. And they're not always right. We've had cases where they've given us certain specifications. We show up, measure, and it's a lot louder, or it could be quieter even. Of course, we don't get called in if it's quieter, but it's louder than the manufacturer is stating. But I mean, that's what we use. We use the information we're given. The better the information, the better our services, of course, or the better our predictions. Anyone's predictions are. But you take them with a grain of salt. They're not always going to be perfect. Not every unit is the same. And we find this for mechanical systems in general, just with time, wear, maintenance, belts, the noise levels can change with time. Plenum, return systems. So this is where we're talking about the return. We see this a lot in open office spaces. They just have open returns with these grills, return grills in the ceiling. And those are fine, but they're really not great where sound isolation is critical. So we recommend they duct the noise. I wonder if I have a little, yeah, duct the noise if you need that RC to be less than 35. If it's a noise sensitive space, if you want quiet, if it's a recording studio, or if it's a private office where noise is a concern, then we'd recommend ducting. If it's not, if it's an open office area, then a lot of times you can get by with that. Rooftop air handling systems, you have a lot of issues right below. So again, you don't want that to be in a noise sensitive area. You have noise, you get breakout from the ducts right below, you have radiated from the unit below, you have vibration, and you have the duct borne. Duct penetrations. This is especially critical if your duct or your mechanical room is right near a noise sensitive room. But you're going to want, whether it's a gypboard wall or a concrete wall, you're going to want non-hardening airtight seals. Noise works a lot like light. If you can see through, if you have a light on in that mechanical room and you're in the other room and you turn on the light and you can see light on the other side, there's a poor seal and there's going to be a noise issue. And you can have a pretty large barrier, and a small opening will dramatically impact or reduce the sound transmission class, or the amount of noise or that it prevents, that it blocks. So small openings can add up and hurt. So you have to be real careful. You don't want them hard sealed, because you can get, the duct will have some vibration. Vibration, really, when noise is perturbations in the atmospheric pressure, it's vibration. And so when noise hits a surface, it's either reflected, absorbed, or transmitted, but it's transmitted as vibration. So if you shake a wall, you will cause noise from the wall, especially a lighter structure would be even more of an issue. So that's important to keep it as isolated from the wall as practical. Here's a diagram about ventilation. We do want, they're saying not recommended versus recommended. You want as smooth of flow over the fan as possible. Now, this is an example of some, a prop, vein axial, one of these, but just as I guess it illustrates what's good, what's helpful. If you have dramatic transitions right near a fan, you're not going to have even flow across the fan. And then the noise levels aren't going to match what the manufacturer is saying. The manufacturers are giving you laboratory perfect conditions where there's, this nice smooth flow going over a fan. Whereas if you have an elbow right next to it where all the airflow is slammed down on the lower portion, or there's dramatic transitions, or they're not equal, not symmetric transitions, you won't be matching that, or offset ducts. The flow will not be even. That'll be a problem. That's the problem with diffusers as well, and we'll get into that. Not recommended versus recommended. Just guides. Again, evening flow, distances. If you're if you do have an obstruction, I guess they're showing here, obstruction on the discharge would add to the back pressure. Again, not helping the acoustic situation. Terminal units, this is a big issue. Okay, so terminal units being the VAV box, whether they're non-fan powered or they are fan powered. And we'd recommend, because we don't have a slide on that, but we'd recommend if it shouldn't be over noise sensitive spaces. If it's a non-fan powered unit, just distributing the flow, again, a unit less than an area where RC35 is required. If it is fan powered, you don't want it above an area where an NC40 or lower is needed. So it could be appropriate for an open office. Of course, some manufacturing or noisier environment wouldn't be an issue, but in quieter areas, they can be a big issue. Of course, we predict, or it's easy to predict. They give you noise data for radiated from these units and duct-borne, and that just gets added in. You have the duct-borne from the primary air handler unit, and then you add in whatever the terminal unit is adding into that. So what issues here? Fan disk turbulent airflow. So yeah, I think that's all I have there. Isolation from buildings, chillers, compressors, pumps. You definitely want to enclose them. These are loud. If they're on a roof, vibration becomes an issue. If it's a noise sensitive area nearby, you might have to float the floors, but definitely spring or some kind of isolator would be needed. And if they are on a roof, if there is some kind of rooftop unit, then the ceiling system, that structure needs to be evaluated, the roof to the ceiling. And I think we have some illustrations. Fan noise control, we've got duct liners, sound attenuators. And when you're putting in a sound attenuator, and those are, do I have pictures? Yeah, I mean, those are sheet metal, solid sheet metal acting as a barrier with perforated sheet metal and fiberglass in between, adding as absorption. It does change the flow, so you have to be careful with self-generated noise from silencers. And the manufacturers will give you that data. And with silencers, they're pretty standard how they're constructed. So if one manufacturer isn't providing that data, you can pull it from another, even if the one you want to use or the manufacturer you want to use it doesn't have that data. But when you restrict the flow, you're going to cause some noise, but then they do a good job of attenuating. And the thicker the liner, I mean, in this case, they're pretty thick amount of insulation, the better it attenuates at low frequency. So if also the longer the silencer, the better it attenuates at low frequency. So duct lining is great for high frequency noise, 500 hertz and above, but it's not going to do as much for low frequency. And yeah, I'm going to stick with that. Silencer placement. You definitely, again, if there's corners, you want to give yourself space. You want the flow to be as smooth as possible going into the silencer. You don't want them real close to a fan if at all possible. Sometimes you don't have a lot of choices, but it will generate more noise. And the manufacturer is giving you the self-generated noise levels for smooth flow through the silencer. So if it all gets slammed to one side or another, that's not going to be as helpful. Silencer location as well. Looking at where it's positioned, this is your ideal situation where there's not any break-in noise coming through. This is not as ideal, and of course this is pretty poor. You have the silencer and then you have an area for break-in noise. And the same at this end, noise will break out, in this case before the unit. You do have some choices here. You could lag or try to absorb or keep the noise in until you get to the silencer if that's an issue, but it's more cost and effort. So turbulent airflow controls. Again, you just want to have a flow that is as smooth as possible. And now we're looking at diffusers. These supplied the discharges. You'd like it, the manufacturers, they're going to give you levels for smooth flow over their discharge. If it's not smooth, if it's all slammed to one side, you're going to get a lot more noise, and you'll hear that hissing or air noise over the diffusers. Yeah, this is the base of the testing, which isn't always what you see in the field, but that's how we select diffusers. We say, they got to be, we add up the criteria in the room. If it's an RC 35 and you have 5 diffusers, each diffuser, has to be below that so that the sum, depending on how far they're spread out, will stay below that 35. And so you select them, and maybe they're at RC 30. That might not happen if they're poorly, if it's not that smooth, the flow over that. Regenerated noise. I guess this is noise from flow because of transitions. Now the modeling software will predict noise from elbows, noise from curves, so you can get an idea ahead of time. But just in general, you want to avoid abrupt transitions. You want to avoid big changes in sizes real abruptly, where you're going to have where you could have some issues. Same with branches. This is the best situation where it's nice smooth transitions versus the worst where you just slam in a 90-degree elbow. So, same here where you have a T. It'd be nice if there was something guiding the flow. Again, if it's not over a noise sensitive area, who cares? I mean, we're more just care about efficiency and flow, but what we're worried about is just the noise being generated by the transitions, and that can be predicted. Offsets, of course, the more gentle, the better, in any transition. And these are some guidelines with the airflow, what kind of flow for what kind of criteria. And mostly what we see is just straight elbows, and it's fine. It can be predicted what the noise generated by that transition is, and if it's an issue, we can tackle it after. So this is what we see as mitigation, or what we provide as mitigation a lot of times for these ceiling paths. It can become costly, especially after the fact, but if a silencer isn't practical, possible, if we're going in after the fact, it might be hard to mess with the ductwork much. And its uses change. Maybe when it was initially designed, the open office spaces, it wasn't noise sensitive, and then they've readjusted it or broken it up into individual offices, and they're more sensitive to the noise. That's fine. So what we look at is just an open grill. Like I said, noise travels a lot like water or light. Just an open grill is not doing much as far as attenuation. The ceilings, they get a CAC rating, which is the noise from one room through the ceiling into that plenum area, down through another ceiling, and that's your CAC rating. It's not just one straight, like an STC, one straight path. But if you have openings in it, that's going to greatly reduce the effectiveness of the ceiling. So in design, there are some conflicting issues with ceiling selection. if it's an open office space or most office spaces, we want this to be as absorptive as possible. But when we're dealing with mechanical noise, we want it to be as, have the highest CAC or highest transmission class. We do not want noise passing through it. And if you have a very absorptive fiberglass ceiling, noise can pass right through it, even though it'll absorb the noise in the room from people talking. Any noise reflected, any noise impacting this will get either absorbed or transmitted up into that ceiling plenum. There won't be as much reflected, but when you're just talking about mechanical noise passing through, a light fiberglass ceiling tile is not very effective. You can also after the fact, or they do have, Armstrong does sell, or manufacturers do sell a system that can be placed on top of a ceiling where you put gypboard and then fiberglass board. Generally, we do see bats rolled on ceilings, and the first time someone goes up to fix something and they push the bats aside, not to say this always happens, but a lot of times they don't get put back into place. And so the effectiveness of those bats isn't, might not be long lived. Whereas if they're glued directly to the tiles, you probably have a better chance that they're going to stay in place because it's one unit. So if someone goes up above the ceiling and moves it and puts it back in place, the whole system should stay in place. Now, if you put these on after the fact, then you have to make sure that ceiling supports will hold the additional weight, because that's adding significant additional weight, especially when you put on a boot and then increase the weight of the ceiling. And then in some cases, yeah, we've had to put gypboard boxes over light fixtures, just because that's a very lightweight metal. Noise can pass through pretty easily. And so if you treat the ceiling, treat the return or the grill with a boot, then this can become a weak link. A lot of times that's not desirable because there could be heat issues or other issues, but we have had to do that in some cases. All right, breakout noise. So breakout noise is a little tricky, not tricky, but low frequency noise transmits through barriers easier than high frequency noise. So breakout noise is generally a very low rumbly noise. The one way to contain the noise is circular duct. The problem is it's just pushing it downstream. So it's almost better to have rectangular duct over a non-noise sensitive area and let that low frequency energy break out and dissipate, and not just get pushed downstream. Because if you do have circular duct, which is very rigid, and if you do increase stiffening, that will help contain that low frequency noise, but you're not absorbing it. It's gonna break into the rooms eventually. Maybe not break out, but it'll come through the duct, or it'll, if it transitions to rectangular duct, it'll break out later downstream. Lagging is another option. And then the silencer. So lagging, there's a few ways to treat. I have a couple pictures here. And then silencers can handle low frequency noise. So you can handle the breakout noise. Silencer's not going to handle breakout noise before the silencer, but if you get the silencer in before it goes into a new room, you know, within the mechanical room or on the roof, then, you know, that will help the breakout noise situation. So one way to, if you have lots of space, one way to deal with breakout noise is to construct really an independent wall. It's nice if it doesn't touch at all. Noise will break out, it'll get absorbed, it'll hit these 2 layers of gypsum, and some will transmit, some will get reflected, and some will be absorbed there. But this will do a nice job of significantly attenuating that breakout, attenuating and absorbing the low frequency noise. If you have 3.5-inch thick fiberglass bad insulation, that will attenuate down to pretty low frequencies, especially if it's a long stretch of that. I guess that's my only figure. We did this a lot where you're just trying to add stiffening to this. You can attach drywall. We actually used aluminum framing at one point to not add a lot of mass, but we're trying to add stiffening to the duct, like a round duct. Again, just be aware that's pushing the low frequency downstream. But if there's a noise sensitive area you just want to avoid, or you're just trying to treat it until the silencer, you have a place for a silencer, then you can, stiffen the duct, and that'll help the noise not break out. This takes a lot of space, so it's not the most practical above a ceiling. We do see after the fact people using loaded vinyl. And the key is to use quilted, or at least put fiberglass down first, then the loaded vinyl. It's heavy vinyl, a pound or 2 pounds per square foot. It's heavy material, so you want to make sure all the supports will hold it. But that, if you do put fiberglass, then the loaded vinyl, it'll do some absorbing, and it's a damped material, so it'll keep the breakout to a minimum and absorb. It's just going to be costlier than drywall, but it'll take less space, easier to install after the fact. Equipment vibration isolation. So to determine the amount of vibration, you can't really just feel. If you're up on the roof and you're just feeling, or in the equipment room and you feel the walls or the floor, it's hard to really determine how much of that is from airborne low frequency noise that is hitting the surface and causing it to vibrate, and how much is actual structure-borne equipment vibration. So a lot of times what we can do is, and the other thing too, low frequency noise is not directional, not very directional. So you can't really hear where it's coming from if you're listening around, or even with a sound level meter. It'll be pretty uniform in a space. It's very long wavelengths. So structure-borne component, a lot of times we have to determine what the other paths are. So if we're dealing with rooftop noise or rooftop equipment, you determine how much is coming from radiated through the system, determine how much is coming from duct-borne, radiated from the ductwork, and if there's a missing component, that becomes the vibration component. You can, with an accelerometer, measure the vibration of a surface, and there are formulas given the amount of vibration, the size of that surface, what level it's creating. Again, it gets a little bit complicated because if it's radiated noise, that's converting into vibration and then radiating on the other side. So at least it would eliminate looking at the duct-borne or breakout noise. You could just narrow it down to the radiated and vibration and see how that looks. And the more information, the better. And if you're in the design phase, that's your only option. Follow the vibration isolation guidelines for the equipment that's being used. And the stiffer the roof system, the better. The closer they're located to structural components, the better. So some of the options you have, inertia bases, and again, ASHRAE manual. A lot of times we use Mason Industries. They're very helpful in guiding what is required. We generally recommend you just use one isolation system. You don't try to double them up because the relationship one to another could cause some problems. You're getting natural frequencies from each, and if they line up, you know, it could be not as helpful as just having one isolation unit. So equipment isolation, what is isolation mounts, hangers, I guess for ceilings, flexible connections. You'd really want that mechanical unit to be floating as much as possible. So even if you put great isolators that it's resting on, if you have hard connections through the ductwork or hard connections through any other connections, you can short circuit that isolation that it's resting on and cause problems or just cause vibration to transfer. It'll pick not that it'll pick, but it'll go through the weakest path. So isolate one path really well and leave another open, it'll not be very effective. You don't want to over compress your isolators. A lot of issues we see are after the fact. I mean, if they're well, or just over optimistic expectations. So you follow the guidelines, you use the isolators you're supposed to, but you're locating unit directly over a noise sensitive area. Well, there could be issues because it's not doing as much as you can. So, okay, isolate all the paths. The ductwork needs to be isolated. If the unit can move, everything needs to be able to move. Environmental noise, a lot of times we see this, and this is when you're looking at mechanical noise radiating to nearby residences or even to the same building through the glass or through the walls. It can be a unit, or it can be an issue. We've had that where generators or mechanical equipment are located down in some equipment yard and a tall building is looking down on it and the noise is radiating without any barriers. Regulations, again, if it's the same building, we're not dealing with regulations. We're dealing with just what's the guideline for that space, what's the path, and how much is it attenuating, and so what do we predict that noise will be on the inside from the outside. It would be nice if regulations were uniform. They're not. Arizona is terrible with regulations. There are some states that have statewide environmental regulations. I used to work in Oregon and Colorado. I mean, I still do, but I used to live there, and they have statewide regulations, which makes it easier for everyone, because instead of having no regulation, you can predict and come up with how much mitigation is reasonable, and so take those steps to make it reasonable. Instead of having no regulation or very stringent regulation or loose regulation or just people complaining with it, we have some regulations in Arizona where if it's audible indoors, that's a violation. Inaudible, or if you get someone sensitive, if you get a very quiet environment, if you get very poor windows, you can have issues. Whereas if you have some property line, 50 decibels at night, 55 during the day, it makes it easy to target. Arizona doesn't have a statewide regulation. We have each city or county, if it's not within a city, has its own regulation. And we see Tucson's regulation is 70, 72. Phoenix will have a 50, 55, reasonable limit. Maricopa County, so if you're in the county but not within a city, it's if it's audible. Flagstaff is if it's audible, which audible is a tough one. There's a bunch of them that are just if it's a nuisance, which again, it's a fun one when you're in court. And so that's what we see with Tucson having such a high level. They don't have an average limit. They just have it can't exceed this higher limit. We see that it's real easy to meet, but if it's actually 70 some dB in someone's front yard, even though it meets the criteria, they're going to complain and they're going to potentially have a lawsuit. I mean, we've seen that a lot. There was grocery stores where we had to reorient or come up with mitigation for rooftop equipment on a grocery store, on a big box store. It's pretty common, but that's after the fact because they really didn't have a criteria to meet in the design phase because it's such a loose criteria. So regulations are all over the place. It's good to check them out before getting too far. It could be as simple as reorienting a rooftop unit, raising a parapet, putting some lined elbow on a discharge or intake. It can be really simple what can get done. Control, again, you have barriers, orientation. If you don't block the line of sight, you're not doing anything attenuation-wise. So back to the building being next to the equipment yard, if you're on the 5th floor looking down at a building, it doesn't matter if they have a 10, 20-foot wall around it. If you can see the equipment, you're done. That barrier is not effective. So the more you break the line of sight, the more attenuation is achieved. Then again, new equipment versus older equipment. Sometimes it's just maintenance. And we see that with mechanical equipment as well, internal HVAC. Sometimes it just needs rebalancing or someone just to look at the equipment, and it's not installing additional mitigation. It can just be maintenance, upkeep there. I think that's about it. It's all going to come together. So just briefly, if anyone needs help, we're here, Noise Expert, we're acoustical consultants. We are independent. We don't sell any products. We work on mechanical noise, vibration, environmental noise, room acoustics, industrial noise, and provide expert testimony when needed, deal with lawsuits more regularly than we should. And we are a DBE organization, if that's helpful in bidding for a project. Any questions? I'm gonna actually cancel the screen share. How do I do that? All right, great. Okay, if you have any questions, if you just type it in the chat, I believe I'll be able to receive those. I am not a master at this webinar stuff, but I'm getting used to it little by little. So questions, I'll put here. I think one question we do see quite a bit is how accurate are the predictions? They are generally conservative when we're modeling, and most software that you'll see is based on ASHRAE just because that's something that's defendable. So, and you could tabulate, just use them. You can actually, the first company consulting firm I worked for, we just used Excel spreadsheets with the ASHRAE tables and just came up with, all right, straight duct, it attenuates at these frequencies by this amount, and just keep running a tally. And then now of course they have programs, free programs even that you can get, and you plug in different components. It'll give you the attenuation. And it's generally conservative. Again, you're relying on what the manufacturers tell you. If everything's accurate, then you're fine. You know, usually the predictions come out pretty good. Sometimes things aren't isolated the way you had hoped, or the unit isn't operating at the levels it should. Then you can run into issues. And again, we'd much rather be in the ballpark at the design phase than deal with the costly process of trying to address issues after the fact. It's cheaper to spend $1,000 to evaluate upfront than who knows what if there's issues after the fact. But to be honest, we mostly deal with the acoustics after the fact. It's generally people put them in, hope for the best, and then just address issues as they need to. And it's just a cost concern. All right, I'm not just going to talk to myself. If there are no other questions, I will end this then. Let me just see what I can do. I think I can push people to a room. Ah, here we go. Thank you. I think this is the thank you page that I want, but it might not be. And I will push you to the thank you page. And then I will, I guess I will end it here. Again, we're noiseexpert.com. Let me know if you have any questions about this or about, you know, anything else acoustics. Be glad to help. Hope you got something out of this. And take care. Have a good day.